to do. The second part will be a bit more intense. So we have the equation, we know what is the incident wave. Now we can state the problem. Let's do it. So let me draw the coordinates. So we have our coordinates L and H. We don't care anymore about Cartesian coordinates. And we have a wave float coming on the surface of the cylinder. So our so we present the total field as a sum of the incident and scattered wave, the incident wave we had before on the blackboard, and on the boundary we have a Dirichlet condition, write down like this. Or in dimensionless coordinate like this. So additionally, contrary to parabolic equation in Cartesian coordinates, we also need to satisfy radiation condition, because we can have on H on H or eta we have a second derivative, so we both can have wave going from the origin and coming to the origin. So somehow we need to take into account radiation condition. This is actually a problematic point for parabolic equation. So I was avoiding it for Cartesian one where it's clear. But so here we don't have a simple way to do it. So we need to improvise, and I will do it on the way. I will show how we do it during the solution of the problem. And okay. Let's solve the problem. We have some reason we have point D, which is solution. And how would have you solved this problem? I will solve this problem using Fourier transform. So it's like so I will get a very formal solution for this problem. And of course we can apply, it's a bit non-standard Fourier transform. It's like the Fourier transform is standard, but we just apply it not in Cartesian coordinate system. But it doesn't matter. We have tau going from minus infinity to plus infinity. Then we can apply it along the lateral coordinates. Nothing stops us. And then we will kind of separate the angular and radial part of the problem, kind of. Or you can say lateral and perpendicular part of the orthogonal part of the problem. But formally, it's nothing smart. We apply a Fourier transform to our equation. Define, so we start from definition of a spectral function. Okay, so we integrated tau equation on tau. What we will get? We will get the following thing. And do you recognize this equation? Probably not, but let me make a change of variables and maybe you will recognize it. It's a very, very well-known equation. So with this change of variables, we will have just an ordinary differential equation. Now it depends on two variables, but of course we can get rid of one of them. Of course, here I should have put tilde or hat because I just changed the variables, but you probably know it's not zeta, but it should be eta of zeta, but I skipped this part to make my notation simpler. I suppose it should be understandable. Okay, have you seen this equation? You know, we have quite a simple equation, simple looking equation. Have you seen it before? It has a name. Any guesses? How many named differential equations you know? You know it. How many named differential equations you know? Ordinary. There is like a basic equation. I like Bernoulli equation. What else? Anything comes to mind? That's fine. If you don't know, you don't know. So it's called Airy equation. Shame on you. Airy equation. And since it has a name, it has a solution. And like one approach, we have this equation, we find a solution from like a textbook, and then we modify the solution in such a way that we have an outgoing wave. And that's what I will do next. Oh, it's from a textbook. Yeah, let's discuss it for a bit. You probably haven't played with it much, but it's very important for diffraction theory. So, one solution is denoted like this, AI. Let's infinity. You also might have seen it before. So this is just from Wikipedia. So maybe you've seen this integral before. It's some oscillatory integral, highly oscillatory. And what should we know about our contour of integration? So we will check that this function satisfies this equation, so you will believe me. But before we do it, let's see how domain of growth and decay of these exponential factors, how they look. Let's draw them, because that's why we are here, to draw some nice diagrams. So, since we have a cubic power here, far from 0, this term will dominate, and growth and decay will be defined by this term. So, what I do, I divide my plane in like 6 zones, and just direct check will show that in one zone so this is the domains of decay, and these 3 are domains of growth. Try, like, I recommend to check it yourself, and of course you can find the location of this line. It's probably pi over 6 or pi over 3 or pi over 3. Yeah. And and our contour of integration, it's actually not the best choice for the contour of integration, because it goes along the real line, and this is where our function is oscillatory. So the integral converges, but does not converge absolutely. It oscillates, and for the sake of safety, and that's probably what's written in Wikipedia, the contour of integration should go like this. So I just slightly deformed it. It still stays in the domain of decay, and I will write, instead of this, I will have here. And okay, we didn't derive this solution, but at least let us check that it is a solution indeed. So let's apply second derivative to Airy function. And since I deform my contour like this, I have an absolutely converging integral. I can differentiate under the sign of the integral. Now I don't have any problems. Shouldn't worry about smoothness. So what do we have? we will rewrite it like this. So I want to make a full differential under the same limit. So I minus plus, so I added this term. I have minus, yeah, I have minus for this. So I added this term and now I need to subtract this term. And this is an Airy function multiplied by z. And this thing is obviously 0. Do you know why? So it's not that obvious after all. Okay, we have a full differential and I can kinda write it like, this thing evaluated at some rotated minus infinity and plus infinity, where this thing is a decaying exponential. So this part will be 0. Of course, this is not the right thing to say. I should consider a limit, but this limit will be 0. Fine? Good. And we just solve. Second derivative is equal to this, so we have proved that this thing is solution to Airy equation. Okay. This equation of the second order, thus this equation should have two independent solutions. And second choice for a solution, this is also some textbook material. Second choice called BI. Contours integration are like this. Just for the reference, I'm not planning to discuss it, but before we can proceed to the solution of our original problem, we a bit strained it right now and we're doing some ordinary differential equation theory, but just taking a glance. We need to know the asymptotic behavior of this solution, and then we need to choose which one of them corresponds to the outgoing wave, the way we understand it. And I won't be doing asymptotic analysis, but it can be done using saddle point method. Maybe I will do it next time. I'm considering whether I should do it. Maybe it's a good exercise. Because this example is quite non-trivial. This function has two saddle points. As you can see, when we differentiate the phase, we will have a quadratic equation. We'll have two saddle points, and we will have different asymptotic behavior depending on how many asymptotic points, how many saddle points contribute to the asymptotic. And but now I will just, one way to find the solution you like is to just plot them. And also that's something specialist in diffraction you should be aware of behavior. Try to draw it. So this is BI. So what I tried to show here, that first of all, for positive z, this thing decays exponentially, this thing grows exponentially. And for negative z, this have some wave type behavior. So they oscillate, they decay slightly, but not exponentially, polynomially. And also the phase shift between BA and I is pi over 2. And if you are smart, you do asymptotics. And if you are not smart, you open Wikipedia and find asymptotics on Wikipedia, which is also okay. And I'm curious about the negative z. So it behaves like this. This is the asymptotic behavior. And if you take a brave person like V.A. Fock, and that's how I think he did it, because he has a whole book on the subject. You can just find, download it, and have a look. It's a very interesting book, but it's quite complicated and very vague. So it's hard to follow his thought process. He just comes up with some solutions, and the solutions tends to be okay. So it's my way of my supervisor to understand this thing. This is how we understood it. And he was smart. He said, okay, this is sine, this is cosine, not exactly what I want. And I just boldly will say that the function I need is like this. And this, he says, okay, this thing should behave as an outgoing wave. So we will have cosine plus I sine, and we will have exponential. And this is how we expect a decaying wave to behave. And this is like outgoing wave, outgoing. And for completeness, we need a second solution. I will just write it down, which is a decaying wave, an incoming wave. That's a bit bold, and of course you need to justify it, but probably the way he did, he have seen it, then he constructed the solution, and then he checked that what he has is indeed a solution to the problem. Probably he did it the other way. But anyway, we finally can get back to our problem, and for the spectral function, we have that spectral function is a sum of these two solutions with some coefficients. I will go back to variables c and eta. And this thing right now known as Fock function. But mostly I think on post-Soviet space. And so we need some uniqueness, since this thing will grow at infinity. We don't want it to grow at infinity. We will treat things, so we will prohibit this behavior, and we will say, okay, we prohibited it, and that what we mean by radiation condition for this particular problem. This is radiation condition. So here we kinda act as creators. We construct a solution we like. So we have some physical motivations. It's like an interplay between physics and mathematics. So how do we find this coefficient? What is the standard way to find the coefficient? No. We integrate over a sphere when we have a Green's function problem. And for this thing, we just, what else do we have in our problem that we didn't check? The boundary conditions. So we can substitute this into boundary conditions, and for boundary condition, we just have 0 here. So what are, so our boundary conditions, if we substitute this form there, with the following structure. So this is a scattered field equal to minus or incident field. on the boundary. So on the boundary, eta is 0. Eta is our orthogonal coordinate. Okay, this is simple integral equation which we solve by Fourier transform. We do the inverse Fourier transform, and let's not skip this step. This thing is precisely the Airy function. We had, last time we had pluses here, but we can go from tau to minus tau, and so we will have the Airy function. So this thing is equal to AI psi by 2 times AI psi just by definition. Okay? Believable, of course we were quite lucky. Whatever we do, we get Airy function. We are very fortunate. That's not how it always happens. Only in some nice cases. And that's it. We have a solution to our problem as a Fourier transform, which is also known as a formal solution. The solution is usually then studied asymptotically. Fortunately, so for A psi, we have minus AI psi divided by psi. And for total solution, final result, which is an amazing VA Fock formula. Oh, this is the A Fock result. Which is quite nice, simply looking, but this thing has a lot of structure. So if you try to study it asymptotically, it's actually won't be a simple study. And for example, from this solution, you can recover all the creeping waves this problem generates. So when the wave fails, then you have, actually it's like a bunch of modes creeping slowly along the boundary of the cylinder, and they behave like Airy. So they oscillate close to the surface of the cylinder, and then they exponentially decay away. So they only exist in a narrow region close to the surface of the cylinder. Oh, I will have a thought whether maybe we will just study this integral asymptotically next time, and it will take the collection if you want. So I think that's it. Thank you. I hope you enjoyed. See you next time. Subscribe, like, and hit the bell.